Let's do a really hard one. Now let's just think about how nasty this would be if we were to do it with the limit process, right? You'd have to go x plus h to the fifth power minus x to the fifth, and then divide that by h.
I wouldn't do that.
Grossness, right? We can all say that that's just a bad idea to do it that way. Okay, there's nice little shortcuts, and one of them is called the power rule, and it's a beautiful thing. This is what you do. You take the exponent, right there, this is the 5. You multiply it by the coefficient in the front, which is a 1. And so my derivative for this function is going to be a 5x. And then you take the exponent, that's the fifth power, and you'd reduce it by 1.
What? Oh my god.
Done.
Done. Is that the one that I figured out?
That's it.
Yeah.
Okay.
Now, the generic for this, the generic looks like this. Okay, if I've got some x to the n power, this is my original function, f of x. This is what the generic looks like. Okay, you take whatever the exponent is, which on this one is n. So I'm going to move the n into the front, and so f prime of x, the derivative, okay, is going to be n times x, and then you lower the n by 1, so it's going to be x to the n minus 1.
Why does that work?
Okay, it's a proof of the binomial expansion with canceling like terms, and then you just kind of see all the patterns that will unfold. So it's kind of long just because that binomial expansion is pretty big.
Well, you're so mean.
Maybe Friday. I think we'll have a little more. Well, actually, Thursday.
Yeah, we don't have to go Friday.
I will. So I have school Friday. Yes, I have school
Friday.
So. I will prove it. But today we got a fair amount to get through. So. I know people will be upset. That was it. Done. Okay, your homework assignment. No, I'm kidding. It gets a little more complicated now. Obviously, now that once they give you a nice little shortcut, they're going to start to make problems even harder, obviously. So, I know. Brutal. So let's do a couple that are a little harder. Nice part is the power rule works for most things. Most. There's obviously exceptions, times that it doesn't work, and I'll have to explain kind of as we go through it. But this one we can do. It's just a power rule is what they're going to call it. They call it the power rule because, well, you're taking the power, moving in the front, reducing it. All of that revolves around the power. There's all these other rules that we're going to be doing, different ways to take a derivative and whatnot. So the first thing I want to do, and they call it a rewrite, but I would just write this as an x to some power. Okay, so this would be rewritten as x to, let's see, a third root would be the same as the 1/3. Okay, so that'd be the same as the 1/3 power. Okay, so if I were to take the derivative of this guy, this takes the place of all that conjugating mess stuff you'd have to do. It should be gross. Okay, so you take the 1/3, move it in the front, multiply by x, you reduce that by a power of 1. Okay, so take 1 off that. So negative 2/3, okay, so negative 2/3. Okay, so it's 1/3 x to the negative 2/3. Now we don't like to have negative exponents, so we do want to fix that. The way to fix that is to go 1/3 to the x to the 2/3 power, and you can just leave it just like that. Okay. Sometimes it's beneficial to get it back into a radical or some kind of cube root or whatnot. If you wanted to, you could write it like this. This would be 1/3, and this would be the third root of x squared. If you wanted to get a little more fancy. I don't care if you leave it like this, though. It doesn't hurt my feelings. Okay, this is just useful to me. So, cool. So if we can get it down to x to some power, we can take the derivative. Okay, so that's or we can just do the power rule and take the derivative of that. Okay, everybody feeling pretty good about that? Not too bad. Okay, ready to go a little harder? I hope. All right, what was that big mess of one we just did a couple seconds ago? It's 1 over x squared.
4 over x.
4 over square root of x. We will do that one. Just to really stick the... This is one we just did, right?
To be really mean.
Just to be really mean, yeah. Salt in the wound, you know. That kind of good stuff. Yeah. Now, my goal is to get this to be x to some power. If I can get x to some power, I'm good to go, right? So how can I get this x squared to the numerator? Negative exponent, right? So this would be x to the negative second power. So x to the negative 2. Pretty good. Now I can use the power rule on that, which is sweetness. So the derivative of this. Just move the negative 2 in the front. Reduce that by power. All right, we're subtracting 1. And then we don't like negative exponents in our final answer, so we just change that. So it's negative 2 over x to the third. Isn't that the one we just did? Okay, awesome. You guys loving the power rule yet? Maybe yes, no. So
Well, I hate it right now.
I figured you would. Okay. Now notice everything I've given you has just been one term. Okay. Power rule also works over multiple terms, but you have to be careful. You have to be either adding or subtracting those terms together. So example of one that would work when you're using this power rule. Something that's a little more complicated, something that's a little longer. I think it was question number 24-ish or so. Maybe I should just do 24. What was 20?
I don't know, 4 was
I don't know.
26 is x squared plus 2x.
Okay, there we go. X squared plus 2x plus 1. Okay, so let's say I want to take the derivative of this guy. And we haven't really talked about a constant yet, what happens there, but I think you guys will be okay with that in a second. Okay. Now, what they want you to do with this big mess, there's another way to write this, taking the derivative idea. A lot of times they call this the function y, obviously. So another way to say I'm taking the derivative of this is to put a little bracket in the front and put a d over dx, like that. That's another way to say that we're taking the derivative of this function. Okay, it's purely notation. All this stands for is I'm taking the derivative of this function. That's what the top d stands for. And then the bottom d says I'm taking the derivative of this function, and they call that with respect to x. That means that x is my variable that I'm taking the derivative of. That'll come into play a little bit more later on what variable we're talking about. That can change as we get on a little bit later. But for now, I'm taking the derivative of this with respect to x, which means x is my normal variable. All rules apply. We can do whatever we want to do here. Okay? So my derivative of this, which would be the same as y prime or the same as f prime of x, all those are the same thing. Okay? I just do the power rule, and I can do it a power rule on each individual term, as long as I'm adding or subtracting between them. So if I cover this up right here, I just do the power rule of 2x, or x to the second. That's just 2x if I take the derivative of that. Okay? So this would be 2x. Now what about the middle term? This is another power rule here. I've got 2x right here. It's to the first power, right? So if I were to multiply, right, 1 times 2 is 2. So this would be plus 2. And then x to which power?
0.
To the 0 power, right? Well, what's x to the 0 power? 1. So we really don't need that part, right? So it's just going to be plus 2. Okay? Now the last term is kind of funny. Technically it's x to the 0 power if you were to do the power rule on this one, which is kind of funny. But when you multiply 0 times this front number, it's going to be 0 plus 0 times x to the negative 1. Well, who cares? Because it's 0 times whatever, right? So if you take the derivative of a constant number, it's always going to be 0 no matter what. Okay? So I'm going to erase this part. So it's just plus 0, which we don't really need to write that, so we can just leave the derivative as this. Okay, 2x plus 2. If you thought about just the graph of just the one part, because you can do the derivative of each individual term, if you thought about the graph of this, that would be this line right here, right? What's the slope of any point on that line? 0, right? Any point in this line is 0. Slope is 0. Okay? So if I take the derivative of this, which is slope, then it's going to be 0. Okay? So 2x plus 2 is my derivative for that. Okay? Now the next part, what do they want me to find on 26? Might as well just finish that one problem. They say find the equation of the tangent line through a point. Okay, what's my point? 2, 6. Negative 3, 4. Okay? So negative 3, 4, this is problem number 26. But if I were to first take the derivative of it, and this one was to highlight each individual term, you can just take the derivative of each individual term if I'm adding or subtracting. Now I can just plug this point in. So if I want to find the slope at this point right here, negative 3, I'm going to go to the derivative at negative 3 equals 2 times negative 3 and then plus 2. So I multiply there, I get negative 6 plus 2, so I get negative 4. Okay? So my slope is negative 4 at this point right here. Okay? Now, does this y value really do anything so far?
Are you supposed to find the equation of the line?
Yeah, I'm not done yet. Yep. But I was just asking, does this 4 do anything yet as far as the slope goes?
No.
All it really cares about is what the x value is and then what's the slope at that x value. Okay? The y value doesn't matter too much until we start writing equations of lines. Okay? Okay, now, there's two ways to do this, and I was debating whether to show this to you guys or not, but I think I'm going to. Y equals mx plus b is kind of the standard way you guys have learned how to write an equation of a line. There's another equation, another form. It's called the point-slope form. Have you guys heard of that before? It kind of looks like this. It's y minus y1 equals m, and then x minus x1. Have you guys seen that before? Probably. Okay, they call that the point-slope form. The reason they call that the point-slope form is if I have the slope and I have a point, I can just plug it into this formula and get an equation for a line. Okay? Now you have to treat this point right here as your x1, y1. That's your first point, your only point. And then this is your slope right here. Okay? Which, if you think about all the problems that we've done so far, we're finding a slope. by using the slope generator equation, the derivative, and then they give us a point, right? So right away I've got point slope. I might as well use this form if you can. So just go ahead and throw that in there. So it's going to be y minus y1, the first y is 4, equals the slope, -4, and then x minus x1, so x plus 3. Okay, now the beautiful part about this is you could solve for x here, so you could solve for y here, get into y equals mx plus b, right? The AP test doesn't care. You can just leave it like that. They can say, yes, that's the equation of a line, you're done. It's pretty sweet, right? Okay, they figure that you guys are far enough in math, you don't actually have to simplify that. And they're okay with that. I'm not making that up. They're totally okay with that. Okay? So you can just leave it like that, or you can do y equals mx plus b. This kind of sucks for graphing. Like if you wanted to graph it, it's kind of hard because our calculators are always y equals. So to check your answer, it's kind of nice to be able to have a y equals equation. So anyways, so that's that. We're feeling pretty good about this power rule. Pretty easy, I hope. Okay, they get a little more complicated, obviously. Let's do one kind of tougher one. What was the super hard one?
4 over square root of x.
4 over square root of x. That one was gross. Took up a whole board. And then I'll show you how the multiply and divide ones work real quick, and then we'll be done. Okay. So I got 4 over square root of x. First, I got to write this in kind of a polynomial term. Okay, I don't want to have a fraction. Fractions and multiplications right now are bad. Okay, so we have to try to get rid of those if we can. Okay. So let's get rid of this fraction. We can rewrite this as 4 x to the, looks like, what, -1/2 power? You guys okay with that? 4 to the -1/2. Just move this term up top. Now I do the power rule. So I'm going to multiply those two together. So 4 multiplied by the -1/2 gives me a -2. And then x to the, drop that by a power. So this is going to be a -3/2 power. Okay, we okay with that? I hope. Okay, then we just fix this negative exponent right here, which we don't like, so we just put that in the bottom. So it's going to give me a -2 divided by x to the +3/2, which is similar to the answer we got before, right?
That's cool.
Yes, it is. Anyways, all right, two last ones real quick, kind of some exceptions, ones to watch out for. If I have like a, just a regular polynomial where you're adding terms together, product rule works power rule works beautifully. You can just go right through it and be good. Sometimes it's not so nice, and we're going to learn some other shortcuts as we go, but for now we have to just kind of watch out for a couple of little things. The first one is if I'm multiplying things together, like if I have x times x plus 1.
Should we distribute that first?
That'd be a great idea. Yeah, if I can get it down to just a regular polynomial where I'm only adding and subtracting between them, then I can use this power rule. Okay, the power rule backfires on this. Too many people, like let's say this was an x squared, they try to power rule the first and power rule the second, and they get all mixed up. And there's actually ways and tricks to do that, and I'll show you later. But for now, if we can get it to a regular polynomial, that's going to be better for us. Okay, so we're going to distribute this x into everything. It's going to give me x to the second power plus x. And now I can just take the derivative of that using the power rule. Just multiply the 2 in the front. So this will be a 2x, drop that by power, so x to the first, plus derivative of x is just going to be 1. So 2x plus 1. Okay, what's up?
What if we get an equation that has, okay, it was like, two fractions, and one fraction is subtracted by another fraction. So,
Give me a quick example.
let's see if I can find one. Did it in the notes. Let's see.
Like that?
Yeah.
Okay, just make this a polynomial, or just make this a 3x to the -1, right? Actually, we can't do this one yet. Sorry. I lied. We can't do that one. We'll get there soon. Sorry. So then just make it this, and then do the power rule on that, right? Put this one up at the top, so it's plus 2x to the -2, power rule on that. Okay? Not bad? Okay. Now the last one is the fraction one, where it's one big fraction, so just got to watch out for that one as well. Let's do this one. Let's say it was 2x to the second minus 3x plus 1 over... Ooh, I can't do this one yet. Yes, I can. I'm just kidding. I got to bump these up a power.
A power or multiple powers?
That's not a power.
Need a little bit more than
This would suck doing it the long way. Yep.
Yeah, we really
Yeah, I'd love to see anybody raise it to the 20th power. Even if you know the binomial shortcut, that's still not fun.
Oh,
That's still brutal. All right, we can't do a fraction yet. Okay, we'll get there. We'll learn a couple nice shortcuts for fractions, although they're not very nice, just so you know. The better answer, the better way to do this is to split this up to give each one its own denominator. So this would be a 2x to the 20th. Divide this by x to the 7th, and then minus 3x to the 19th divided by x to the 7th, and then plus x to the 5th divided by x to the 7th. Okay, so giving each one its own term is a good thing. Now we can try to simplify as we go a little bit here. So if I divide, I can just subtract those exponents. So it's going to give me 2x to the 13th power. And then minus 3, this would be x to the 12th power. And the last one plus, this is going to be x to the negative 2nd. Okay, so effectively I'm just dividing that x to the 7th into all three of them, getting down to what looks like almost like a polynomial, just that negative exponent's the only thing that makes it not a true polynomial, but it's pretty close. It's in that general form. Now I can just do the power rule here, so my derivative of this function is just going to be, looks like 26x to the 12th, minus, this would be 36x to the 11th, and then plus, or I guess it would be minus here, minus 2x to the negative 3rd. And then just make this negative exponent go away. So just put that in the denominator. So we get 26x to the 12th minus 36 x11 and minus 2 over x to the 3rd. Okay? Now if you really wanted to make it kind of look like the original equation was in this format right here, you could do that. You could give each of those a common denominator, give them x to the 3rds, put them on the top as well, and then you can group those all together. Okay? I don't really care if you do that. It doesn't hurt my feelings. Okay? All right, so we feel pretty good about this. It's not too bad. Very nice shortcut, considering. All right, cool. The homework shouldn't take too long.